Hi there and welcome back to the triplicate digital synthesis tutorial and part 8. In the last tutorial we got our filter working and got to the point where the development version of the synthesizer would play a few musical notes, actually sounding like a synthesizer. In fact, sounding like this. Now we're developing the mean green hardware synthesizer in parallel with these tutorials, and the plan was to get the basic synthesizer working in the mean green hardware. In trying to do this, I discovered the code was running far too slowly. In trying to speed it up, I found that the STM32 we were using in the mean green has a built-in hardware floating point. I'd selected this particular processor solely on the basis of the clock speed it was capable of. And I hadn't even noticed this. So up to now in these tutorials I've been suggesting that wherever possible we should work in floating point, but I've also been describing methods of using integer arithmetic. Given the state of the current technology and the fact that it can only get better, I've decided to concentrate from now on solely on floating point ways of doing things. And at some point I will upgrade the earlier tutorials. Right, shall we have a look at an LFO? There are lots of waveforms and nice features that we can incorporate into an LFO, but for now we're just going to go for the most popular waveforms: triangle, sawtooth, square and sample hold. So first let's generate some waveforms. All the waveforms use a simple phase value, which is incremented every sample by a value dependent on the LFO speed control setting. This is simply looked up from a table to give an LFO period which ranges between 100 milliseconds and 10 seconds. So first the triangle wave, which is the most complicated. The output depends on whether the phase, in red, is in the first quarter, the middle two quarters or the last quarter. Note that the LFO always produces a signal output between -1 and +1. The square wave, in green, is simply -1 or +1, depending on whether the phase is less than a half or greater than a half. And the sawtooth wave is calculated simply and directly from the phase value. If we want a descending sawtooth wave, we simply apply negative modulation, and we'll come to this. The sample hold wave generates a new random value every time the phase value rolls over, and every time the phase value passes a half. This is because the square wave changes every time the phase value passes a half. And sample hold sounds a bit slow if it only changes every time the phase value rolls over. Okay, let's now move on to a common feature of LFOs, and that is LFO delay. A musician, say a violinist, when applying vibrato will generally start the note at a constant pitch and then bring the vibrato in after a small delay. Now we can imitate this using the LFO delay feature. Here we have the output of a triangle wave LFO with delay. So what's happening here? Well, we've got three notes here, one after the other, so we'll consider the middle one. At this point we have a note on, so the LFO delay starts. So now for a third of the delay period there is no output from the LFO at all. And then for the remaining 2/3 of the delay period, its output level ramps up to its maximum value and then stays there for the duration of the note. Okay, so here's a few notes with an LFO applying continuous vibrato. The delay is set to 0, so the vibrato is on all the time. And now let's play the same notes with an LFO delay applied. As I say, I shall return to the LFO when we consider performance features. We might also see if we can make the delay work more musically and maybe even add a couple of interesting waveforms. For now, we're going to move on and have another look at parameters. So, as I said earlier, we tried to run our code written for the PC development stroke test application, and we tried to run it in our mean green synthesizer, and it was taking too long. So we need to look at ways of speeding it up, and one of the ways we could look at is the parameter system. Now, if you read anything about writing software, they will tell you you need to use some kind of object-orientated system, if at all possible. This allows the code to be written in chunks or objects with defined inputs and outputs, which means you can test it. Define the object and its interfaces and test it, and then we know how that's going to interface with other objects, etc., etc., rather than having a huge great chunk of code, and if it doesn't do what it's supposed to, we don't know where the problem lies. So we created a parameter object which takes all the control rate signals like potentiometers and MIDI and envelopes and LFOs, and does everything we need to do to them, and feeds the result into a sound creation or modification module, for instance the filter cutoff. And we tried to create a parameter that would do any job. So we had, it can have a number of inputs, which it sums together, it smooths those inputs, clips them to a range and converts them to some sort of an output. But we have to make things go faster. So what we need to do is simplify this and have more hard-coded special cases, i.e. more code to go wrong, but that will run faster. So to do this, we have actually created two types of parameter. We have a modulation parameter that has a pot and can have modulation from envelopes, LFOs, etc. And we have a potentiometer kind of parameter, which basically just takes the current pot value and converts that into some number and applies that. Okay, let's look at the modulation types first. Again, it can have a number of inputs, but whereas before we could use possibly different smoothing algorithms, here it's hard-coded in and it's smoothed and ranged, and any conversion is then some hard-coded function within the sound creation or modulation module. And the inputs are of three different types. We can have an input which is just a pot setting, an input which is a modulation from an LFO or an envelope, where the pot here is the modulation amount and they're combined together to be a value, or we can have a direct input, for instance pitch bend would be an example of that. Okay, the pot type, we simply have an input from a pot which will be 0 to 127 because we're working in MIDI terms here, and then that is converted to a value appropriate to what it's doing, usually by looking it up in a table. And since effectively the parameter is just one input and the parameter itself doesn't do anything, we just reduce that to one input. Reduces the number of function calls to go into a parameter. Okay, so just a quick look at the code. Here's the modulation parameter. So we go through the inputs and we multiply a scaled val by a source pointer. In the case of modulation, which that source pointer just points to a value of 1 for pots. Then we smooth it. The smoothing code is now built into the parameter. Then we range it, we make sure it's within range, and that's done. So that's a lot neater than the code was. And if we go into the filter, we look at the top here. So it's called that function to update the parameter, and then it's called paramout interpolate, which just takes a table and takes that output and converts it to what is essentially a logarithmic output using a table. So that's pretty simple. And for a pot style parameter, every time the pot value changes, this function is called for its appropriate parameter, and we normally have a table which it just uses to look up the value, or it can simply scale it and subtract a 0 off if it's a very simple one. And if we go into envelope, you can see I've highlighted that in the attack phase. It just looks up that table val from the input. Simple and efficient in code. And so now finally to panning. Okay, here we're only trying to implement a basic auto panning effect, so I don't propose to go into the theory of panning in any detail. There's plenty of information available on the web. However, we should note that because we actually hear sound intensity, which is the sound amplitude squared, if we want to pan a mono sound evenly across a stereo field, the left and right levels should look like this. Now, to implement this, we would need to do two interpolations from a sine-cosine curve stored in a table. This would use up a significant amount of our precious processing time. So we are going to use linear panning instead, which requires only two simple scalings. This will accentuate the far left and far right of the stereo field, but since we are most likely using the auto pan for effect, this will actually accentuate the effect, which is probably going to be good. This makes panning simply a parameter with a set pot and a modulation source. Okay, and there we have it. We update the pan parameter and use scale the mono output by the output of the pan and 1 minus the output of the pan, which is pretty simple. So what does our pan effect sound like? Here we have a basic little sequence panned with a triangle wave, and it sounds like this. Okay, there we go. That's it for panning, really. And that's it for this synthesizer development tutorial video. In the next Mean Green build video, I'm going to have another go at getting the synthesizer code we have developed here working in the Mean Green hardware. And this will include the move to floating point, the changes to parameters we discussed here and modulation, and we'll add the LFOs and panning. And next time we're going to look at some performance features such as auto glide and portamento and get them working, and we'll also take a look at polyphonic operation. So until then, leave a comment if you've got something to say, thumbs up would be nice, subscribe if you've found this interesting, and for now it's goodbye from Triplicate, home of interesting electronics. Goodbye.